9:41. It will, not be 9:41 for another 9.5 hours, 10.5 hours, something like that. Does anybody know why it says 9:41 at the top of the screen? This only happens when you're doing screen sharing of an iPad on a laptop for display on something like this. If you do it with an iPhone, it says 9:40. Does anybody know why? This was a feature specifically engineered into iOS at the request of Steve Jobs. Because at the developers conference, when Apple announced the iPhone or announced the iPad, it was scripted to be exactly 41 minutes into the presentation that started at 9 o'clock. And rather than deal with the fact that the clock might be in the wrong time zone or might display the wrong thing, they just hard-coded it to say 9:41. That's also the reason why it says over here in the other corner 100%, even though it might not be. And it's also why on the upper left corner I'm getting fantastic Wi-Fi. All right, so don't be distracted by the time at the top of the screen. It's not the real time, it's the ghost of Steve Jobs. All right, welcome back to the second lecture of 374. Since a couple of people have been asking, let me first talk about a few minor administrative things. One, if you have been looking at the course website, you might notice that now there's a Google Calendar at the bottom of the front page, where the TAs and the course assistants and I have been filling in our times for office hours. So we already have, I will have my first regular bit of office hours this afternoon at 4 o'clock over in the third floor of Siebel. I'll also be available out here in the hallway immediately after class. One thing that I put in there is I will have regular Tuesday office hours out in the hallway immediately after class that just happens to coincide with the date that homework is due. But if 300 people come crowding around me asking for the solution to problem 2 out there, it's not going to work. So my Tuesday office hours are specifically for questions not having to do with that week's homework. It's to handle all the other kinds of things that people need office hours for. I was completely lost in lecture. My grandmother died. I'm going to have to miss the midterm. I broke my arm. Can I turn in my homework late? Some weird thing happened in lab that I need to vent about. I'm worried because my grade is not as high as I'd like, and I'm wondering what to do. All those discussions that people absolutely have to have with an instructor of a course can't happen when there are crowds of people around asking about problem 2 on the current homework. So that's the intention of the Tuesday office hours for me. Thursday, it's perfectly fine to ask homework questions. Yes? If there are no other higher level questions pending, you're welcome to ask about the following week's homework. Because then you might think about it more than a week in advance. So that's good. So watch as those fill in. I'll warn you, since this is the beginning of the semester and people's semester schedules are still in flux, the office hours that you see there this week might not be there next week or the week after. So things may be a little bit dynamic, but just watch the web page. I've explicitly told my TAs that it's a bad idea to have office hours on Tuesdays because homework's due Tuesday evening and we know what happens. Corollary, do not start the homework on Monday. I'm hoping that people will actually bring me questions about homework 0 this afternoon. The class is going to start moving fast. Please, keep up. Otherwise, you're like, if you keep up, it should be okay, but if you get behind, it can really be a problem. Second thing about turning in homework, Homework will be submitted online using this program called Gradescope that I talked about last time, and you'll upload a PDF. One way to produce the PDF is to download the LaTeX solution template and type your solutions in LaTeX. If you don't know LaTeX, you can probably extrapolate from what's in the solution template already. For most things, there's lots of resources on the web that you can learn it. If you don't want to learn LaTeX, that's fine. You can just write your solutions on paper, take a picture with your phone, run it through some sort of scan app to get rid of the part of the picture that has your cat in it and the frilly bits down the side from your spiral notebook, and does some contrast adjustment. And then just upload that PDF. Just please make sure whatever you upload is readable. The graders get to decide whether you were successful. If you upload something that isn't readable, the graders don't have to try to read it. But when I do this on my phone, I use an app called Scannable. There are dozens of these apps that will work. Please also, it's helpful if you write in pen. It's helpful if you don't have lines on the paper. But the main thing is just please make sure that everything you want to say is readable and everything you don't want to be part of your solution is gone. I think that's all the administrative gobbledygook I have to talk about, unless there are questions. Yes? I'm not sure what you expected to happen since there's nothing to grade yet. Okay, so when you sign up for Gradescope, you need to supply a name and an email address. You can use your real name and your university email address, but this is just meant to be a unique identifier for you. Okay. And then when you submit stuff, you will say, this is me, this is my school name and email address, and we'll grade it, and then at the end of the semester, we'll attach that grade to your actual university records. It's pretend that you're handing us paper. We haven't given you anything yet with your grade on it because you haven't given us anything. Same thing. Any other administrative questions? Okay. So, what are we going to talk about today? Hopefully the quotations give it away, or maybe you actually look at the schedule. We're going to talk about languages, and in particular, regular languages, and the strings of text that we use to represent those regular languages, which are called regular expressions. Now, language as a noun suggests things like English or Java or Klingon, or something where it's not just syntax, but it actually has semantics. But when we're talking about languages in this class, what we actually mean, and sometimes this is emphasized by putting the word formal in front, formal language is just a set of strings. Okay? So, the empty set is a language. The set containing the word football is a language. The set containing the words football and BMO is a language. The set of all words in the Oxford English Dictionary is a language. The set containing the string the space Oxford space English space dictionary is a language. The set of all Python programs that compute hello world is a language. The set of all strings over a particular alphabet is a language, right? So language here is really just a fancy way of saying set, but a set of a particular type. Okay? So sort of canonical examples to think about here. Let me throw up three particular languages that are useful as edge cases when you're thinking about these things. The first one is the empty set. And since this has already come up on Piazza, let me emphasize that is not the Greek letter F. The empty set symbol was introduced in the 1930s by a mathematician named Andrew Weil, who was part of this collective of anonymous mathematicians who published under the name Nicolas Bourbaki. Bourbaki tried, as a collective, to establish formal foundations for all of mathematics. There's a similar, you might have heard of Whitehead's Principia Mathematica, where he spends 500 pages proving that 2 + 2 = 4. It was like that, only more verbose. It infected French mathematics for decades after. American mathematicians seem to have shaken it off for the most part. But that symbol was modeled not after the Greek letter phi, but rather after the Norwegian letter. It's a barred O. It's roughly pronounced Okay? See the empty set? Right? Keep that in mind. This is not a phi. Do not pronounce this phi, or God forbid, phi. Do not use the Greek letter \PHI in your LaTeX. The name of that is \empty set. So this is the set containing no strings. Sigma star is the opposite. It's the complement of the empty set. This is the set containing all strings over the alphabet sigma. Now, this is a template for lots of different languages because every different alphabet sigma is going to give you a different language sigma star. Okay? But if I fix my alphabet sigma, and typically I'll do this by saying sigma is just zeros and ones, sigma star then would be the set of all binary strings, including the empty string. This third thing, though, this third language is the set containing the empty string. It is not empty because it has a string in it. It's the empty string. Right, if this is confusing, think of sets as boxes that you put things into, and strings as bags that you put things into, and this is a box that has a bag in it, and the bag doesn't have anything in it. Okay? It's the set containing the empty string. It's not itself empty. It's different. On the other hand, this symbol is not a language. It is a string. It's a bag. It's not in a box. Okay? This is a different type of object than any of the objects above it. Even though it's an empty object, it's not the same empty object as the empty set. It's very, very easy, especially starting out, to get these two things confused. Just remember, variables have types. And when we talk about strings, use only variables of type string. And when we talk about languages, use only variables of type language. Okay? Okay, good. Now, because strings are sets, because languages are sets, languages can be defined and built and combined with each other exactly the same way that any other set can. So I could define, for example, a set of languages as, let's say, strings over the alphabet 0 and 1, such that W has an even number of ones. Right? So the standard set builder notation that you've probably seen in other mathematics classes, the thing on the left of the bar basically is a type declaration. In this case, it's saying it's a string over zeros and ones. The thing on the right of the bar is some condition that strings in this language have to satisfy. Of course, I can also write, strings down explicitly. Either just by writing them down. But there are other things that I can use to define strings. So I can write a language as the union of two other languages, or I can write the language as the intersection of two other languages. Or I can write language as the difference between two languages. So this backslash is the set version of minus. This means everything that's in A but isn't in B. This is the same as writing A intersect the complement of B, which means, of course, I have to be able to write the complement of B, which I can think of as all strings that are not in A. Okay, so you can do things with languages that you can do with any set in terms of combining them, in terms of writing them down. Yes? Star. Yes? Okay, so this is the set of all strings over the alphabet 0 and 1 that satisfy this condition. So it's a set of these objects satisfying this condition. These objects are strings, so this is a set of strings. This object here in the middle of the set builder notation, here, that is the name of a language. Okay, so I'm taking elements of this set that satisfy a certain condition. So what I'm getting is subsets of, I'm specifying a subset of this language, 0, 1 star. Okay. But now because, come on, thank you. These are not just arbitrary sets, but sets of strings. There are a couple of other operations that you can use to build larger languages out of smaller languages. So the one that is a little bit easier to grasp is concatenation. I can describe a language L to be the concatenation of two other languages, which I will sometimes write explicitly with a big dot if I really want to emphasize the concatenation operation. It's more common just to write one after the other, just as it is for strings. This is defined to be all strings W over whatever alphabet you want, such that W equals XY for some X in A and some Y in B. So if I want to give a specific example, abrahocus dot cadabrapocus, right? This is a language that contains 4 strings. Abracadabra, oh, I should have said that abraca and pocus, so to mirror the Looney Tunes. Abracadabra, abrapocus, hocus cadabra, and hocus pocus. Okay, 4 strings. 2 on one side, 2 on the other. The number of strings you get in concatenation, if the 2 strings are finite, if the 2 languages are finite, excuse me, is the product of the number of strings in A and the number of strings in B. Because you have an arbitrary choice for what you want to choose in A and an arbitrary choice for what you choose in B to give you a string in the concatenation L. So let me test some sanity here. What is that? What is dot L? What is the empty set, the empty language concatenated with L? What does that give you? No, it doesn't give you L. How do you get an element of this concatenation? Well, any element in this concatenation I can compose by taking an element of the first set and putting it together with an element of the second set. How many different ways are there to do this? 0, because I can't choose an element of the first set because it doesn't have any elements. So the empty set concatenated with L is the empty set. On the other hand, what is this? The set containing the empty string concatenated with L. This is L. Because if I choose an arbitrary element of the first set and an arbitrary element of the second set, well, the first one is the empty string, and if I concatenate it onto whatever I chose, I get that string again. Any string in L, I can write down as the empty set dot that string. Okay, so this is L. Again, the empty set is really empty. The set containing the empty string is not empty. If I have n things in the set L and one thing in this set, the number of things I get in the concatenation is 1 times n. Whereas over here, I got 0 times n. Okay? And it doesn't matter what L is when you do this. The other operation that's important to keep in mind when we're building up languages is this star operator. This is known as the Kleene closure of the language. What you should think of this as is the set of all strings that you can get by concatenating 0 or more strings from L. Okay, think of this as iterate L as many times as you want, including none. Right? So an informal description of this is the empty set, union L dot L, union L dot L dot L, union, and so on. Okay. More formally, you would say that W is an L star if and only if either W is the empty string or W is X dot Y or some string X in L and some string Y in L star. And you'll notice this, yes, this is a recursive definition. And as usual for recursive definitions, I require that the recursion must bottom out eventually. So every string in L star is finite. Every string in L star is composed by concatenating a finite number of strings in L. I don't care which ones at any given time, but the strings in L star are still strings. They're still finite. Yes? Well, yeah, you're right. Thank you. Let me emphasize this. Right, it should be the set containing the empty string, not, unioning with the empty set doesn't do anything. The L star always contains the empty string because I can always create the empty string by concatenating 0 elements of L. Okay? So, for example, if I write 0, 1 star, I'm using the Kleene closure operator here, the Kleene star. Right? 0, 1 is a language. It contains 2 strings, each of length 1. And then the star operator says, take any number of things you want out of this language, and with any number of copies of those things you want, and concatenate them together in some order. In particular, I can pull the empty string out of here by not concatenating anything, or concatenating 0 things. Okay? So that star operator that I used to go from sigma to sigma star, that was this operator. Okay? So, sanity check. Is this language, L star, always infinite? So if I start with 0, 1 star, this is an infinite language. It contains every string of digits you want of arbitrary length. And so it seems clear that this language is infinite. Right, I can describe more strings than any number you name. Is that always true? Hint. The obvious answer is, of course it is, which is why you should be suspect, because if that were really true, why would I ask the question? Yes. I'm sorry? What if the alphabet is empty? Well, what if L is empty? Right? So the answer is no, because the empty set star is not infinite. What is it? What is the empty set star? It's the set containing the empty string. See there, right there? So, how do I build the empty string out of elements of the empty set? Easy. I start with none of them, and I do nothing to that, and what I'm left with is the empty string. It's perfectly fine to use 0 elements of the empty set. As soon as I try to use 1 element of the empty set, that's where things go wrong. Okay? Somebody show me an empty sequence of giraffes. Thank you. You've all successfully used 0 giraffes. The fact that there were no giraffes to use is immaterial. Okay? So the empty string is always part of the Kleene closure. This is the only counterexample to this. As long as L has at least 1 string, L star will be infinite. Because I can repeat that string as many times as I like. Yes, in the back. Okay. Okay, good. Thank you. I was wrong. There is another example. The Kleene closure of the set containing the empty string only contains the empty string. Because no matter how many empty strings I glue together, nothing plus nothing is nothing. I still get the empty string. Thank you for the correction. Any language that contains at least 1 non-empty string has an infinite Kleene closure. In English, people normally pronounce this as clean. That's not how he pronounced it. His family was German. In Germany, this would normally be pronounced Kleine. That's not how he pronounced it. He pronounced it Kleine. Clay-knee, not like clean, wash your hands. As his son pointed out, no, this doesn't make any sense. But nevertheless, that's how he pronounced it, and so by definition, that is the correct pronunciation. Kleine. Okay. So, can think of some examples here. Can anybody, I mean, here is an explicit description of a language that I've built by taking the union of 2 singleton languages and then taking the Kleene closure of it. This is the set of all strings over the alphabet 0 and 1, in which every block of 1s has even length. So I can have 2 1s in a row, or 6 1s in a row, or 42 1s in a row, but I can't have 17 1s in a row. Because there's no way, unless there's another one after it, there's no way to make 17 1s by gluing 11s together. Right, so this is strings of 0s and 1s where every run of 1s has even length. Okay? This is a simple example of something that I will refer to for the rest of the semester as a regular language. A regular language is something that can be constructed out of singleton sets by unions, concatenations, and Kleene stars. Okay? So a regular language is either the empty set, a singleton, the union of two languages that are both regular, the concatenation of two languages that are both regular, or the Kleene closure of a regular language. Okay? Now, it turns out that I could include in the definition, without changing the languages that this definition covers, I could also include other set operations like intersection or complement or difference or symmetric difference or anything else. For now, however, we're going to stick to unions because reasoning about things with subtraction turns out to be more complicated. It's sufficient to define things this way, and it's relatively natural to define things this way. Now, I want to give a bit of intuition about why this is a natural object to think about, and in particular, why this is a natural object for computer scientists to think about. And I want to sort of match up the different types of features in the construction of a regular language with things that you might encounter in an execution trace of the program. Right? So imagine that you have, some program that's, got some lines of code here. Maybe it's got some loops. Maybe it's got some if statements. I'm not going to worry too much about the contents of the line of code, except I am going to insist that we're thinking specifically about code, one, that doesn't have any go-tos in it. It's completely structured. And two, I'm going to ignore function calls. I'm just going to treat them as single lines of executable code. Okay. And I want you to imagine that you're going to start running the code and you're going to try to reason about all possible ways of executing this chunk of code. As in saying, okay, first I'm going to execute line 1, then I'm going to execute line 2, then because of the if, I'm going to skip to line 7, then I'm going to run line 10, 12 times, and then I'm going to look at line 11. Okay? So a singleton, this is just a line of code. Right? I say I have a block that contains a single line, and when I trace through that block, I execute that line and I'm done. Right? Actually, if you really want to be a bit more expansive about it, maybe you can think of this as a block of code that just has no branches and no loops in it. So it's a string of lines instead of just a single line. Okay. Concatenation is sequencing. My block of code can be naturally broken into a first block and a second block. And if I'm tracing through the block of code, I'm going to first trace through somehow the first block, and then later I'm going to trace through the second block. Okay. What about union? What is union? Either I trace through block A or I trace through block B. When might that happen? I have an if. Right? Or more generally, I might have a case or a switch statement, and I'm going through more than two possibilities. Okay? So this is conditional. So I could think of some large block by saying, if some condition, then I'll trace through block A, else I'll trace through block B. This is, the traces of this block of code are all possible ways of tracing through A and all possible traces of B. I'm ignoring the fact that this might be a statement itself, but I can deal with that by sequencing, by saying, okay, maybe I need to concatenate a singleton onto the front of this. And then finally, what is the Kleene star? in capture? It captures loops, right? So I'm going to see this block of code. It's inside a while loop. I have no idea, because I'm not smart enough to actually understand what the code is doing, except at a syntactic level. I have no idea how many times this loop is going to be executed. Maybe it's 0, maybe it's 75. But it's going to be some natural number. So if I'm trying to account for all possible ways of executing the code, I just say, okay, fine, whatever, however many times you want to do it, that's going to be legal, right? And of course, you can nest these things and stack these things. You never just execute one line of code at a time. You can stack up 10 lines of code where the 5th line is actually a while loop that contains an if statement, that contains a for loop, that contains an if then else statement. And the same is true for building up regular languages. You can nest these constructions arbitrarily. I can take the Claney closure of the concatenation of 2 languages, each of which is the union of a bunch of things, some of which are Claney closures of concatenations of unions, blah, 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 et cetera, and so on. Okay. So this is a fairly rich set of behaviors that we can allow, but it's not arbitrary. I can't capture all languages using this kind of definition. The prototypical example of a language that's not regular is the set of strings that contain a string of some number of zeros followed by a string of the same number of ones. And at some intuitive level, if I think about tracing through the code, what this is saying is I can't tell from the syntax of the code without trying to understand something that the first loop is going to execute exactly the same number of times as the second loop. That requires being smart, and I'm not smart. I'm a computer. I'm dumb. Okay? Another way of thinking about this is I can't recognize this kind of string without remembering something like a counter that can have an infinite number of different values. Whereas I could recognize in principle something in this regular language by just walking my fingers through the code and saying, yep, I could have done that. And the code is the only memory that I actually need. Right? This distinction between memory and not memory is going to be really important when we're thinking about this stuff. Now, normally, people find this kind of notation with all the parentheses and brackets and unions and so on a bit cumbersome. And so that we've adopted a convenient shorthand where we drop all the braces, we drop the parentheses unless they're needed for disambiguation, and for historical reasons, we use a plus instead of a union. That notation is called a regular expression. Okay? So a regular expression is either the empty set or a single string or A plus B or AB or A star, but with parentheses to disambiguate things. So a canonical example here, 1, 0, star is not the same as 1, 0 in parens star. The first one is a 1 followed by any number of zeros. So the star binds tightly as higher precedence than concatenation. Whereas this is a string consisting of any number of 1 zeros. So empty string, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and so on. This is essentially the form of the kind of notation that gets used in computational applications of regular expressions. This is what shows up when you're writing a compiler and you need to parse the language that your code is written in. Under the hood, somewhere inside the C compiler, there's a regular expression that stands for things like an arithmetic expression or Actually, no, that's not good. Comments, that's a good one. How do you recognize comments? Well, there's a regular, it turns out the language of all C comments is a regular language. And so buried inside the parser for C, there's a regular expression that says, if you see something that matches this, it's a comment, ignore it. You also will see this if you have the misfortune to have to program in Perl or PHP or any of those other nasty languages that involve, very, very complicated versions of regular expression matching. Those languages incorporate additional features into the vocabulary of what a regular expression can do. So they'll have things like character classes, and they'll have sub-expression matching, and they'll even, some of them have even like local variables. Those things are not really regular expressions, at least for purposes of this class. For this class, you saw that's the definition of a regular expression. Nothing else. No new variables, no new weird stuff. You can do all kinds of wonderful magic with regexing, but a regex is not a regular expression. It's its own descendant. It's a different species of object. Yes? Can you say the first one again? Okay, this is different from 1 plus 0 star. Oh, yes, that's right. So this expression over here that I've just written on the right, this is the same as 0, 1 star, because I've just written it as 0 union 1 parens star. Okay. Yes. So this is the way, if you want to write a regular expression for all strings of zeros and ones, this could obviously go in either order. I'll point out that this is not the only way of writing this. And one of the things that makes thinking about regular languages difficult is that there are multiple ways of writing down a regular expression for the same language. So this is a good example. This is any string of zeros and ones. Okay? So let's imagine in your head your favorite string of zeros and ones. If your favorite string is the empty string, great, we covered it with the outer star. Okay, so think of your favorite non-empty string of zeros and ones. It starts with some number of zeros, there may be none, but that's a number, followed by some number of ones, and again, that may be none. But I can capture at least the first character by saying, it's some prefix of my string has the form 000111111. And so I will capture that prefix with this expression 0 star 1 star, and then the rest of the string will be captured recursively by the Kleene closure. Yes? Let me say this string again, 0, 0. Okay, so this thing, so this is the point, this is my point about memory. This string belongs to the language 0 star 1 star. This string also belongs to the language 0 star 1 star. It's not the same string, but I don't care. Remember, I build this up by concatenating an arbitrary string from the language with another arbitrary string from the language with another arbitrary string from the language, as many or as few times as I want. That's correct. The star is not applying to the string. The star is an operation that you apply to a language. It says, in the first step, if you want to do something, pick any string out of the language and then recurse. Right? So there's no memory here. The first and second and third strings don't have to be the same. Yes? The star is different from the power set. Okay, so power set takes a set and it gives you the set of all subsets. right? So the type of object that the power set function gives you is a set of sets. The type here is set. I take a set of strings, I put a star on it, I get a new set of strings. It's not a set of sets of strings. It's a set of strings to set of strings. Yeah? Yes. Right. So in particular, I could also write this string as the concatenation of 4 strings in 0 star 1 star. Namely, the empty string, and then 0, 0, 1, 1, and then 0, 1, and then the empty string. I could sprinkle epsilons in as many times as I want, as long as that number is finite. And epsilon is also in this language because of the star. Yeah. Okay, so this is an excellent question. Why would anyone use the form on the right rather than the form on the left? And the answer is because you thought of the form on the right first, right? One of the things that we're going to be doing is coming up with regular expressions for languages that are described to you in English. And I want it to be very clear from the outset, there is not a unique right answer. There are multiple right answers. And depending on how you think about breaking that language down, it may be more natural to say, okay, look, I'm going to divide the strings in my language up into chunks where I can easily write down a regular expression for one chunk, and then just put a star around it. Okay, and in this case, that chunk was strings of zeros followed by strings of ones, whereas in this case, that chunk was one symbol. But a priori, we don't know which one of those is going to be more natural, more comfortable, so fine. We may end up with something that is somewhat more verbose than we need, but that's fine. This is something I'm going to say over and over again. Don't worry about making your regular expressions short at the beginning. First, make it work, then make it work fast. First, make it correct, then make it concise. Okay? The first order of business is just to get something down. All right, so let me maybe go through just a couple more elementary examples, and then I want to talk about proofs. I wanted page, thank you. Okay, so the easy direction is take a regular language and tell you what it means in English. So this is usually not something that people struggle terribly with. So let me go the other direction. Or let me start by doing a couple examples of this. What is this language? What is this? What language does this regular expression represent? Let me get some. Strings of zeros where the length is at least 4. Okay? What's this one? Yeah. Right, strings of zeros where the length is a multiple of 5. One of these contains the empty string. The second one, not the first one. Okay, so let's try something in the other direction. Strings that alternate between zeros and ones. So 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, the empty string. What I mean here is I never see the same symbol twice in a row. Okay. So the first thing I want to recommend when you're faced with a problem like this is to try to break out easy cases, or at least try to separate things out into different cases that may have a bit more structure than just the language that you're faced with in complete generality. So one thing that might be helpful here, for example, is to think, I'm really kind of uncomfortable with the idea that the empty string fits in this language. Oh, that's just weird. It's making my head hurt. So I'm just going to pull that out as part of my set. And now the rest of it is non-empty strings that alternate between 0 and 1. And now maybe I'm also a little uncomfortable with strings of length 1 because, well, there's not really an alternation there. Okay, fine. Just write them down. Write them down. Now I want strings of length at least 2 that alternate between 0s and 1s. Now I can think of 2 possibilities for how one might classify these 2 strings, these strings. Can anyone suggest a further way of breaking things down into cases? Yeah. Okay, good. So I can break this into start 0, end 0, start 0, end 1, start 1, end 0, start 1, end 1. Okay, so great. Okay, so can somebody give me a regular expression for the set of all strings that start with a 0, end with a 0, and alternate between 0s and 1s? Yeah. Okay. Good. That covers that, because I can let the empty set cover, pull the empty set out of that star, and I'm just left with the bare 0. Okay, good. We're getting closer now. How about a regular expression for strings that alternate and start with a 0 and end with 1? Yeah. Right. So, good. 0, 1, star. Now put the plus there, and now I can get rid of the empty string. That made me uncomfortable. I'm glad it's gone. Okay, so we seem to be about halfway there. At this point, hopefully, I might recognize that the last 2 cases are exactly like the first 2 cases, only I've swapped 1 and 0. And so I can essentially just copy them down. So plus 1, 0, star, plus 1, 0, star, 1, and that allows me to get rid of my lone 1. And so there I have a regular expression. Now, after the fact, maybe I want to write this out linearly instead of having it stacked up. Fortunately, I have this magic whiteboard that lets me do that. There's my regular expression. Now, once I've got the regular expression in front of me, there are things that I can do to make it more concise, which is itself not necessarily a virtue, but the point is there may be things that I can do to make it more clear what's going on. So, for example, you'll notice that I have like this 0, 1 star in 2 different places. So maybe what I can do, maybe it's clearer to actually write this as 0, 1 star followed by either 0 or nothing. And then similarly on the other side, 1, 0 star followed by 1 or nothing. The same expression. So I've got this interesting sort of something or nothing at the end of the expression, but then I think, wait a minute, these things are symmetric. If I reverse one of these strings, I get another one of these strings. So why am I putting the choice only on the end instead of on the beginning? And so if I stare at this a little bit longer, it might eventually occur to me that I can write it more succinctly like this. At this point, I'm being clever, which means this is the point where you stop. Okay. Yes, you had a question. So the question is for the first regular expression. So 0, 0, 0, 0, 0 in the first one. 4 zeros, yes. Because the last star binds to the 0 by itself. So I must have the 4 zeros, and then I can follow it with any string in 0 star. So 4 zeros, 7 zeros, 28 zeros, but not 3 zeros, not 2 zeros, right? At least 4 zeros. Right. The star binds to so the star has higher precedence than the concatenation operator. Think of it like multiplying polynomials. The star is like an exponent. If I write down xy squared, that means x times y squared, not xy squared. Yeah. Give me the example string again. Okay, so the question is 0, 1, 0, 0, 1. Okay, so which expression are you saying that this matches? No, there's an alternation at the top level. That means either it's 0, 1, 0, 1, 0, 1 any number of times followed by 0 or not, or it's 1, 0, 1, 0, 1, 0, 1, 0 any number of times followed by 1 plus 1 or not. The line above it, well, which of these 4 expressions does it match? The plus has the lowest precedence, just like a polynomial. X plus y squared means x plus y squared, not x plus y squared. Plus does not mean concatenate. Plus means one or the other. Yeah. Yeah. Right. The order matters, right? And I think one way to think about what's going on is that's useful to have in mind, and it's useful to have in mind especially when you want to practice proving things, is that regular expression is convenient notational shorthand. The expression with braces and unions and parentheses and so on is convenient notational shorthand. What it's shorthand for is the process for constructing the language. So it's really, really useful to think of that process as a tree. You take your atomic components, your sets that contain individual strings, and you combine them. Notice what my hands are doing. You combine them into larger things, which you combine into larger things, which you combine into larger things. You build up a tree. This is what your high school teachers should have taught you when you were learning algebra. This is what an arithmetic expression really is. It's a program for taking in stuff at the bottom and giving you something out at the top. So when I write this down, so this regular expression, by the way, this is no way obvious. This regular expression is all binary numbers divisible by 3. Of course. Why wouldn't it be that? But to point out what this means, notice that the top level expression here, the least bound operator, the least precedence operator is the plus. That's the thing we're going to do last. So that's going to represent the root of our tree. And what this says is that this language is the union of the language represented by this subtree on the left and the language represented by the subtree on the right. This node here represents concatenation. The language represented by this subtree is the concatenation of the language represented by the left subtree and the language represented by the right subtree. Now, it's really hard to type trees. It's not so hard to draw them unless they get really big, especially if you're using software to do it. It's really hard to type them. So one of the things that you have to do, just like when you were learning algebra, just like when you were learning calculus, when you read the formula, you read this, and what goes into your mind is that. At some level, you have to be able to think, you have to be able to see this structure when you look at this expression. In particular, when you're writing code, and inside your C code, you've got an arithmetic expression or a logical expression. This is exactly what the compiler builds. It literally builds a tree representing that expression. And that is how it manipulates the expressions internally and how it finds things like, you've got x plus x in there, and x doesn't have any side effects, so I can freely replace that with 3 times x. Right? It's manipulating these trees. So I don't know why this isn't taught earlier, maybe because trees are scary, but maybe because recursion is scary, I think is the right answer. But this is the mental picture you should have when you read this. And when you write down regular expressions, what you're doing is you're transcribing that tree using an in-order traversal, remembering to put parentheses in the right places. Okay? So, these regular expressions, they're recursive structures. This, by the way, is why we want you to take 173 before you take this class, is so that when I say it's just a tree, you go, oh, right, I saw those in 225. I saw those in 173. When you're dealing with regular expressions, and in particular when you want to prove something about regular expressions, well, they're recursively defined objects, so how do you prove things about them? Okay, let's try that again. They're recursively defined objects, so how do you prove things about them? Okay, induction. So if I wanted to prove something about an arbitrary regular expression, it's really a tree. What is my inductive hypothesis going to think about? Subtrees. Or if you want to be a little bit more expansive, smaller trees. Trees with fewer nodes. Okay? But generally speaking, when you're doing this argument about the recursive structure, your induction hypothesis refers to the pieces that you recursively glue together. For strings, we can encapsulate this by length. When I'm dealing with regular expressions, if you really are more comfortable thinking about doing induction with integers as the induction variable, you can take the size of this tree to be the definition of the size of a regular expression. And you can do, say, smaller regular expressions, meaning fewer nodes. I do want to emphasize the number of nodes in this tree is not the same as the number of symbols you need to type. Could be bigger, because we write down the bullets for concatenation explicitly. Could be smaller because we don't write down the parentheses. So if I want to prove something about regular expressions, I'm going to follow the same induction template that I followed for strings. Now, it looks long, and that makes it look scary, but I want to point out that it is exactly the same template. So if I want to prove all regular expressions are perfectly cumulate, whatever that means, then I start by writing down, let R be an arbitrary regular expression. Because, of course, I'm proving something about all regular expressions. That's the only thing I can do, is pick one and prove something about it. And then the next thing I would do is I'd write down the last line of the proof, except, of course, I screwed it up. Sure enough, the regular expression that I picked is perfectly cromulent. Then I would say, okay, I'm probably going to be doing something by induction. So I'm going to write down my induction hypothesis. And because I'm dealing with this recursive structure, the formal way of saying this is assume every proper subexpression of R, meaning everything that's represented by a subtree. I could have instead here said every regular expression smaller than R, and that would have been perfectly fine, as long as I remember that smaller refers to this number of nodes in that tree. Okay, so I write down the regular, an induction hypothesis that reflects the recursive structure of the object I'm proving something about. And now I need to write down cases. Now, the definition of a regular expression has 5 cases. Either the regular expression is empty, the regular expression is a single string, the regular expression is the is the addition of two regular expressions, it's the concatenation of 2 regular expressions, or it's the Kleene star of some regular expression. And so I have 5 cases. And so I write all this down. And only at this point do I bother to look up to think, what on earth does the phrase perfectly cromulent mean? All of this is written down without knowing anything, without bothering to think at all about what we're trying to prove. Because it's all boilerplate. All induction proofs have exactly the same structure. But then in these different cases, what I need to prove here is I need to prove that the empty set is perfectly cromulent. And down here, I need to whatever that string W is perfectly cromulent. And I need to prove S plus T is perfectly cromulent. And here I need to S dot T is perfectly cromulent. And here I need to show that S star is perfectly cromulent. And hopefully the definition of perfectly cromulent will say something that will allow me to apply the induction hypothesis to S and T in case 3, and to S and T in case 4, and to S in case 5, each of those being shorter subexpressions. Okay, so in the last few minutes, I want to walk through one proof to give you an idea of seeing the structure in action. But I do want to emphasize here, the reason why this is scary is because it looks like an awful lot of work to write this down. So on your homework, if you ever have to do this, write the boilerplate down, store it in a text file, which then you can copy paste into your homework. Because it's always going to be the same, except for this phrase, perfectly cromulent. And you'll have to do some search and replace for that. And then, yeah, you have 5 things to prove instead of 2, but 5 is only a constant. You can do it. Okay? You have to write 5 functions instead of writing 2 functions. But each of those proofs is likely to be just definition chasing and applying the induction hypothesis. It's really not going to be that bad. Okay? So here's what I want to prove. Just to give you an example. Theorem. Every regular expression without the empty set symbol in it represents a non-empty language. Okay? If I write down a regular expression and the symbol does not show up anywhere in it, the language that regular expression represents contains at least one string. Okay? Everybody understand what the theorem is saying? Okay, so proof. Let R be an arbitrary regular expression. Therefore, the language represented by R is not empty. Okay, I want to point out something about notation here. Most of the time, I'm not going to distinguish between a regular expression and the language it represents, for exactly the same reason that I don't distinguish between 2 plus 2 and 4. They both represent an integer. Okay, fine. But sometimes I need to talk about the representation itself, the fact that 2 plus 2 is an integer, a plus, and a 2. Right? So when I'm reasoning about these regular expressions, and in the back of my head, I'm really reasoning about these trees. I'm not talking about the language so much as I'm talking about the structure that I use to build the language. So I'm going to use this notation L of to make it very clear. At this point, I'm talking about the language that this expression represents. Most of the time, this distinction isn't necessary. But when I'm doing these proofs, I want to be extremely careful. Right? So this is I'm just, putting on a life jacket here to make sure that no one's confused about the type of objects that we're talking about during the proof. Okay. Assume every proper subexpression of R represents a non-empty language. Okay, warning sign, I did something clever. What did I do that was clever? Right, I did not write down, assume every proper subexpression of R that does not contain the empty set symbol represents a non-empty string. And why didn't I do that? Why do I not need to say that? R doesn't contain any empty set symbols. Therefore, no proper subexpression of R contains any empty set symbols. So I could write that it doesn't contain any empty set symbols there as a qualifier, but the qualifier would be redundant. So I apologize for being slightly non-mechanical here, but it's okay. There are 5 cases. Bullet R equals the empty string, R is a single, or the empty set, sorry. R equals A plus B, R equals A concatenate B, and R equals A star. Okay? Yes? Yes, R doesn't contain the empty set string. So, what's the proof for case 1? Proof is this case can't happen. Done. I'm just being careful and mechanical, so I write down all 5 cases, and then I woke up and think, oh wait, that case is redundant. So I write down that case is redundant, but I do that to make sure that the reader is not going to be confused by the absence of that case. You're making a proof about regular expressions, you need to consider all 5 possibilities. Oh, yes, thank you. Yes, I did leave out that very important clause without the empty set symbol. Okay, so, all right, let's go to case 2. Suppose the regular expression consists of a single string. I need to prove that this regular expression represents a non-empty language. Can somebody please give me the proof? The language of that regular expression is the set containing that string. Look, it's not empty. Good. A or B. Okay, so both A and B have no empty set symbol in them. So by the induction hypothesis, the language of A is not empty. Therefore, I can pick an arbitrary element of A, and then that element is also in the language of A. That element is also in the language of A plus B. I could have also picked an arbitrary element of B. Fine. Okay. Next, A dot B. Again, the induction hypothesis implies that the language of A is not empty and the language of B is not empty. So I can pick the string W from the language of A, and I can pick the string X from the language of B, and then the string WX, it belongs to the language of A dot B. Finally, last case, how do I prove that the language of A star is not empty? It contains the empty string. And we're done. Notice, I didn't set out at the beginning to say those are the base cases and these are the inductive cases. When the smoke cleared, I realized I didn't need to invoke the induction hypothesis in case 5. Who cares? Right? The base case in this instance included all regular expressions with the top level node as a star. This is all repeated in the notes, so if you're frantically scribbling these down, both these things that I'm showing you on the screen and more written out stuff will be in lecture notes, which are on the website. With that, I think we're actually a couple minutes overdue. Thank you for your patience. You can come up and ask after. Come on. It's part of the definition. The empty set is a regular language.
But you won't write that.
You will if the language you want to talk about is the empty set. How else would you write it down?
The question about the line with the tree on it.
Yeah.
Oui, oui. Test.
Let's go out to the lobby because we got another class.